In this video, I'll be talking about the Fresnel coefficients for reflection and transmission, where transmission is also known as refraction. When a light wave is transmitted or reflected, the electric field of the transmitted or reflected light has a smaller amplitude and different phase from the incident light. So if we look at an incident beam of light traveling from N1 into N2, let's call this EI, the reflected or refracted light will have a smaller amplitude and a different phase from the incident field. So here you can see the wavelength of this beam is much greater than the wavelength here, and the same with the amplitude. The amplitude of this wave is much larger than the amplitude after it has crossed the interface between the two media. And this happens regardless of what the refractive indices of those two materials or media are. And this is due to the Fresnel coefficients for transmission and reflection. You can think of these as the toll that the wave has to pay at this interface. And these are given by where T is the coefficient for transmission and is dictating the fraction of the incident light that gets transmitted, and the same goes for R, where R is dictating the amount that is reflected at the interface. Now, both of these coefficients, T and R, are functions of the refractive indices of the two media, as well as the incident angle, theta 1, and the refracted or reflected angle, theta 2. If we consider a beam traveling from air, where n is approximately equal to 1, into glass, where n is approximately equal to 1.5, the amount of light that is reflected at the glass surface depends on not only the angle of incidence, theta I or theta 1, but also the polarization of that incident light. And now there are two types of polarization. There is S-polarized light, where the electric field is perpendicular to the plane of incidence. And here you can see that the plane of incidence is defined by the normal to the surface and is always bisecting along that normal. And so if we take a look at the S-polarized light here, you can see that the electric field vector is now perpendicular to this plane of incidence. On the other hand, P-polarized light is when the electric field is parallel to the plane of incidence. So here for P-polarized light, that electric field vector is now parallel to this plane. So this plot shows the fraction of light reflected at this glass surface as a function of the angle of incidence. So we're looking at R as a function of theta I. And this shows for both R parallel, or the reflected light that is P-polarized, parallel to the surface, as well as the reflected light that is perpendicular, or S-polarized. Now notice that at normal incidence, or at 0 degrees, there is no such thing as S or P polarization. It's just linearly polarized light. But for P-polarized light, something special happens. There is an angle here known as theta B, or Brewster's angle, and this is the angle at which no light is reflected.